and see how it all went for you. And then you have a chance to practice one more time with number 5. So with this one, when you first look at it and you see limit as x approaches, this is going to be really interesting, Santi. We're going to see a cool connection between what you're talking about. It's kind of a reverse situation, but it has some similarities for sure. So you start this out and you say, all right, limit as x approaches 0, right? So you can see in the top clearly you have 0 minus 0, and in the bottom you have sine of 0. And so you could maybe jump to this and say the limit of the top is equal to 0, and the limit of the denominator is also equal to 0. And of course that triggers L'Hopital's rule, like so. That make sense? Mm-hmm. Remember, that's the right way to show it there. You want to show limit of top equals 0, limit of bottom equals 0. I'm going to be really careful that we use really good notation there. Okay, so we can say, therefore, L'Hopital's rule conditions met, and I'll try to use L'Hopital's rule. So this would be limit as x approaches 0. Derivative of the numerator is 3x squared minus 12. Derivative of denominator is cosine of 3x times what? 3. That's right, don't forget the chain rule here. Still in effect. And I think we can see right now, pretty quickly from the numerator, that we're done with L'Hopital's rule. I don't know what the answer is going to be exactly yet, but L'Hopital's rule is not going to be used again because the numerator is going to end up being negative 12. So I can now put equals negative 12 over, what's 3 times cosine of 0? 3. So this limit ended up being negative 4. So then we'd say, therefore, our original limit as x approaches 0 of this original lovely expression also equals negative 4. You guys remembering this okay? It's been a while. Any questions? Okay, so one of the things about L'Hopital's rule that we don't often talk about a lot because it just doesn't come up very often in the examples that we do. And so I want to approach, I think this is really a good maybe topic for the group. L'Hopital's rule works as long as the limit actually exists. As long as the limits you get along the way actually indeterminate, and you end up with something that exists. So this one up here on the board is actually something off of the homework. And so it'd be really easy to get confused as to why what's happening is happening. I think this is kind of the heart of your question. When you look at this, would you guys agree with me that the limit of the top is something, and the limit of the bottom is something else? So let's do the bottom first. Infinity minus pi is essentially what? So here is where L'Hopital's rule is actually not appropriate. When you look at the limit as x approaches infinity of the numerator, what does sine do? So limit as x goes to infinity, we're talking about the way far right edge of the graph, way past Cherry Hills, way past Daniels Park, way over there. What does sine do? It just keeps doing that. Doesn't it just keep going? Just keeps oscillating between negative 1 and 1. So this right here, I don't think we can say this, right? And so since that's true, L'Hopital's rule, not in effect. So to take this and say, hey, derivative of top is cosine, and I think this is where you were going with this, right? Derivative of bottom is 1, and so, gosh, how does that, because your question is valid, well, that doesn't make any sense. You said, I don't think this makes sense because I got a 0, and blah, blah, blah. So I think because L'Hopital's rule condition was not met, we really can't use it. So what do? Right? I think there's a couple of ways you can approach this. I think there's 3 ways. Number 1 is a graph. And I think you would find that if you graph this, sine of x over x minus pi, I think you'd get, I might butcher this a little bit, but I think you'd get something like that. where you're still going to see oscillation, but the oscillation is going to go from here to 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 here. And eventually you're going to say, wow, it sure looks like that graph long term is heading towards a y value of 0. You could also, along those lines, make a table, right? So you could say x is whatever it is, 1, 10, a million. So heading up towards infinity. However you want to like divvy up your table, it's up to you. And then of course your y would equal whatever, this would be heading towards 0 eventually, and you'd say, hey look, those y values, they seem to be jumping around a little bit, but the jumps get closer and closer to just being 0. And eventually you would say, looks like we're heading towards 0. Here's another way. Think about it like this. Kind of piggybacking off these. Couldn't you look at this, knowing that you can't use L'Hopital's rule, couldn't you look at this and say, well, think this through. If the numerator forever is simply just going to jump between -1 and 1, this is more of a philosophical way, like it'd be harder to get this on paper unless you wrote a whole paragraph about it. But if the numerator is just going to jump between -1 and 1, but the denominator is going to get bigger and bigger and bigger and bigger, couldn't we say that the numerator is essentially held constant somewhere between -1 and 1? And if the denominator is getting gigantic, aren't we heading towards 0 for the overall value? Mm-hmm. So you can look at it philosophically too. But yeah, you really can't use L'Hopital's rule because of that.
So if we don't have a calculator to plug the numbers in or to graph it, what do we do?
The philosophical way. You'd have to look at it and you'd have to have a really rudimentary knowledge of sine of x and say, well, I know that the biggest sine could possibly be as 1, and the smallest it could possibly be is -1. And so if I know that sine is always going to be some number in between there, but the denominator is going from 1 to a billion to a trillion to a bigger and bigger and bigger and bigger,
yeah,
the overall value of the fraction is closing in on 0. So you have to do it more philosophically.
How do you prove that?
How do you prove that?
Like if we had to because you have to write out the proof for y, because or else you can't just jump line.
Yeah, so at that point you'd have to turn to maybe a table. Like if you don't know the graph, you could always do a table. Think of it like this, it's really not that much of a stretch. If you did a table and you used unit circle-like angles.
Okay, I mean, I think what I'm asking is would you put this on a non-calculator section?
I don't know.
Because if we didn't have
I tend to not answer questions directly about a quiz or a test. You asked me how would I do this without a calculator.
If we had to because you don't want us to jump a step or skip a step, so you can't.
If I asked you to justify your answer, sure. Yeah, I agree.
So how do we justify the answer?
Make a table.
If we don't have a calculator.
You can do the unit circle, right?
Okay.
Please, for goodness sake, don't try. Mr. Anderson, I tried to plug pi over 19 in, and I just didn't know what that was. I'm going to say pi over 6.
Got it.
Or 7 pi over 2.
Okay.
Stuff you do know.
Appreciate it.
Does that make sense?
Yes.
Yeah. So you can start to kind of answer your own question. Do you really think that I'm going to give you a question on a quiz or test in which the only realistic way for you to do it is to spend 15 minutes making a table?
No.
No. But might I give you the tools that you need to construct the stuff you need to be logical about it and do something like this, but given enough tools where you don't have to spend 15 minutes building a table? Yeah, for sure. So try to understand, I don't know that I would give you something with the level of detail where, like I said, literally 15 minutes later you're finally done with your table and you're like, I think I got it. I'm going to give you tools where if you can understand the significance of them, you'll be like, oh, look, oh, and look, oh, answer is 0. And that's because the graph does this and the table says that because I gave you a table, or I gave you some other tool to use. So, yeah, I'm not interested in making you jump through like that. It's take way too long. Okay, other questions on that stuff?
A snake.
Okay, so remember, before we do this final example, I want to remind you that probably the type of question that is squandered the most on an AP test or one of my tests or quizzes, especially starting off, is a L'Hopital's rule question. Not because people don't know what to do, but they forget how the correct way is to write the conditions being met, right? And so take this last opportunity here with, I think, number 5, and practice using some good notation with your conditions and see if you can come to a good conclusion for that one.
How do you know when it's L'Hopital's rule?
If the conditions are met. So the conditions literally have to be limit of numerator is infinity,
So should we always start?
limit of denominators. Yeah, so start with checking that, right? So And like I've said before, of course, these are like zeros and infinities, so it might feel a little different. But with any limit, I suggest you tried like a direct substitution concept immediately. And if you try it in the numerator and you get a 0, you should be like, I wonder if this is going to be a L'Hopital's rule question. Oh, look, the denominator headed towards 0, 2, and that's where you get into that good notation. Your question is extremely valid. How do I know when to do L'Hopital's rule? It's only when those conditions are met. That's a very important question. We conducting the orchestra? I don't know what this means.
We're just trying to figure out the natural log, what it looks like.
Oh, okay. Like the graph or what?
The graph.
The graph of natural log?
Is it up or down?
It's like this.
Oh, it is.
Okay.
It's like an exponential reflected over the y equals x. Let me understand. Oh, that's why you're asking. Okay, had to ask. So yeah, I mean, obviously you can graph this yourself if you want to see a better graph, but essentially ln of x graphed looks like that. Goes through the point 1, 0.
Does that have the asymptote?
Vertical asymptote right there at the y-axis, yeah.
Horizontal.
I think you should figure that out yourself. Because if there is, you'd want to know where it is, right? And all that good stuff. So it's worth investigating. I think you are all worthy of that. Can I give you a hint? Think about, I really do, really important to bring back like Bailey's question. She said, how do we know when it's time to use L'Hopital's rule? And that's really the essence of the challenges that students have with getting credit and showing that they do know exactly the answer to her question. And it really comes down to just one answer. Were the conditions met? Like, do you know the conditions and were they met? So remember, the conditions are the limit of the numerator is 0, limit of denominator is 0. That's one of the conditions. Or limit of the numerator is infinity, limit of denominator is infinity. If you get either of those two conditions, then it's L'Hopital's time, right? Okay. So let's just be really careful with notational stuff. Yeah.
So when we first started, to give us a list of like other things that could like come back to like infinity over infinity. Will we ever see those?
So that's outside the framework of our course.
Okay.
Those certainly are interesting, and they do come up from time to time, but not in our course. So, yeah. So please don't spend any extra energy working on those unless you're just curious. And it's like basically if you can do a logarithm, if you can do like the natural log of both sides of an equation, you can handle it. So I think you can handle it. It's just that'd be a whole day of energy spent that I'm like, as interesting as it is, we don't really need to. So don't worry about it. Hey, so Andy's question, Eden's question about what does the graph of ln do? I hope you figured out that ln, even though it does it really slowly, doesn't ln continue to increase? Forever and ever and ever. Really slowly, but it does continue to increase. And so the limit of the numerator as x goes towards infinity is infinity. And the limit of the denominator as x goes towards infinity is the same thing. So how do we know when to use L'Hopital's rule? Well, the conditions were met. We have the limits heading towards infinity, both top and bottom. So I'm going to say, therefore, L'Hopital's rule conditions are met. So I'm going to use L'Hopital's rule. And again, please just be super careful. I didn't make a big deal about this. We've talked about this in the past, but this was also an issue. Make sure that when you continue on, make sure that limit as x heads towards infinity, make sure that doesn't pull like a disappearing act. Make sure that stays there until you actually do the thing that it told you to do. So as I attempt to use L'Hopital's rule, limit as x heads towards infinity of 1 over x over 6x. I've done my two derivatives. You really could make a judgment here if you really wanted to. You could manipulate this a little bit further and say, well, this is really copy.flopped would be limit as x heads towards infinity of 1 over 6x squared. Like I said, I really think on either one of those two places you could make a judgment on this one. The bottom line is, isn't the denominator getting really, really large? Numerator is held constant, and so I think we're heading towards 0. So we could then close it off by saying, therefore, the original limit is also heading towards there. Andy, what's your question?
Well,
So say again, if you take the derivative of what?
And then of x is like 1 over x.
Right.
And then x goes to infinity.
Yep.
So doesn't that kind of mean like there is kind of like a
Like-
horizontal asymptote at infinity?
So what you're basically saying is 1 over x, of course, is the slope
Yeah,
of ln of x.
yeah.
And so if we just took this and did kind of a separate little thought and said limit as x heads towards infinity of 1 over x, certainly you do get 0. What that means, though, is that as x gets bigger and bigger and bigger, the slope of ln gets closer and closer to 0, but does it ever actually reach 0? No. Remember, a limit is a pattern. So what this means, think about it like this. What this doesn't mean that f, I'll just call ln of x f of x. It doesn't mean that f prime of infinity equals 0.
Yeah.
Because there is no point 0 comma infinity on the graph of ln. So to say that the long-term behavior is that it flattens out, you really can't. All you can say is that, and even really looking at this derivative here, you could say, well, I do know for sure that as x gets bigger, 1 over x heads towards 0, but never actually equals it. Remember, a limit is simply the pattern of behavior.
Yeah, but isn't it just like an asymptote?
No. No, because, so, okay, so here, you're talking about two different graphs. So let's see here. This might be a good comparison. If I were to draw the graph of, sorry, my x and y axis were all skewed. That's a little closer. So if I were to look at a graph of natural log of x, it looks like this. And if I were to look at a graph of its derivative, as you know, 1 over x does this. Oh, sorry, that's not a very good graph. Come on. Does that make sense, Andy? Okay, so if I say the limit as x heads towards infinity of natural log of x, if I just looked at it from this perspective, I would say that as x gets bigger, this continues to go up. It never stops moving up, and so there is no upper bound.
Yeah, I know.
Right.
Like, what I'm saying is like at infinity. Like,
So stop right there. That's your problem. At infinity. Okay, Buzz Lightyear. You see what I'm saying? Like you're saying, okay, when we get to infinity, the behavior will be, that's the fundamental flaw. That make sense? Am I wrong?
Yeah, no.
So I don't think we can say the moment we get to infinity, it's like me saying, hey, the moment I get to be 1 billion feet tall, like whatever comes out of my mouth next makes no sense because that's just not going to happen. So I don't think we can say at that moment because there is no moment. Does that make sense? Okay, cool. I love your question. It's a really good question because it gets into the nature of what we're actually doing. It gets into the nature of what a limit actually is, which a lot of people struggle with. So you're asking great questions. Really, really good questions. Others? Anybody? No? All right, cool. So let me stop this.